Hey everyone, welcome to another deep dive. Today we're going to be exploring the life and work of Lester Germer, a physicist who played a key role in proving that electrons, those tiny particles we usually picture zipping around atoms, they can also act like waves.
It's one of those concepts that really makes you go,
It really does. It's this mind-bending idea called wave-particle duality. And to guide us through this, we'll be looking at an essay by Jorgo Schneeppert. It's titled Lester Germer, Mitentdecker der Elektronenbewegung, which translates to Lester Germer, co-discoverer of electron diffraction.
Perfect title.
So let's set the stage.
Yeah.
We're talking about the early 20th century. The world of physics is in a state of upheaval. Classical physics, which had worked so well for centuries, was starting to show cracks.
It's like they had this beautiful puzzle, and they thought they had all the pieces, and then suddenly they find a few pieces that just don't fit anywhere.
Exactly. Things like black body radiation and the photoelectric effect, they just couldn't be explained with the classical model.
These phenomena, they were hinting at something deeper, a more complex reality at the atomic and subatomic level.
And that's where Lester Germer enters the picture. Born in Chicago in 1896.
Schneeppert tells us he was a curious kid right from the start.
Oh, yeah. His family really encouraged that scientific curiosity. He went on to study at Columbia University, learning from some of the best physicists of the time.
And then, and this is a crucial step, he joined Bell Laboratories.
Ah, Bell Labs in the early 20th century. What a hub of innovation.
Yeah, a real melting pot of brilliant minds, pushing the boundaries of science and technology.
It was at Bell Labs that Germer met Clinton Davisson, and together they embarked on an experiment that would change everything.
It all started with a seemingly simple question. How do electrons bounce off a nickel surface?
Sounds pretty basic, right?
You'd think so. But as we'll see, even the simplest questions can lead to the most extraordinary discoveries.
So tell me, what exactly did they do in this experiment, and what did they find?
Well, let's start with the setup. They had this nickel target, and they were firing electrons at it.
Like a tiny electron gun.
Exactly. They wanted to see how these electrons would scatter off the nickel.
I'm picturing like a ricocheting bullet.
Sort of, but remember, we're in the quantum world. Things work a little differently down there.
Right, of course. So they fire these electrons at the nickel target. What happens next?
So they're firing these electrons, and something unexpected happens. There's an accident in the lab.
Oh no, what happened?
A flask of liquid air explodes. It breaks their vacuum tube and exposes the nickel target to oxygen.
That doesn't sound good.
Yeah, you'd think it would ruin the experiment.
Okay.
But it actually turned out to be a lucky break.
Really? How so?
Well, to clean the nickel, they had to heat it to a really high temperature.
Okay.
And this heating process, without them realizing it at the time, actually changed the structure of the nickel.
So they inadvertently altered their target.
Exactly. They went back to their experiment, firing electrons at this newly treated nickel.
What did they see?
What they saw was an interference pattern.
An interference pattern, like what you see
Yeah.
when you throw two stones in a pond.
Exactly. Those ripples you see, they interfere with each other, creating those characteristic patterns.
So you're saying these tiny electrons, which we think of as particles, they were acting like waves.
That's exactly what they observed.
Wow, that's mind-blowing. It's like those electrons were rippling through space.
It really challenged the way people thought about electrons back then.
Now, this idea of matter behaving like waves, it wasn't completely new, right? Didn't Louis de Broglie propose something similar?
You're absolutely right. De Broglie had this radical idea that all matter, not just light, has wave-like properties.
I remember learning about his equation. Lambda equals h over p.
Yeah, that's the one. It relates the wavelength of a particle to its momentum.
So de Broglie had the theory, but Davisson and Germer, they provided the experimental proof.
Precisely. Their experiment gave concrete evidence for this mind-bending concept of wave-particle duality.
It's amazing how an accidental discovery can lead to such a profound shift in our understanding.
It's a testament to the power of observation and being open to the unexpected.
I mean, it really makes you question what we mean when we say something is a particle or a wave.
It blurs the lines, doesn't it?
It definitely does. So this experiment, it firmly established wave-particle duality as a cornerstone of quantum mechanics.
And it had a ripple effect throughout physics, leading to new theories and even new technologies.
Speaking of which, I can't help but think about Schrodinger's equation. That equation is like the foundation of quantum mechanics, right?
It is. And
Yeah.
you know, the Davisson-Germer experiment actually played a role. in its development.
Really? Tell me more about that.
Well, Schrödinger's equation, it describes the wave function of a particle.
The wave function?
Yeah, it's a mathematical description of the state of a quantum system, in this case a particle like an electron.
Okay.
And this wave function. It gives us the probability of finding the particle at a certain point in space.
So we're not talking about knowing for certain where a particle is. We're talking about probabilities.
Exactly. That's one of the key differences
Yeah.
between classical physics and quantum mechanics. In the quantum world, we can't know both the position and momentum of a particle with absolute certainty.
It's like there's a fundamental limit to what we can know about the world.
That's right. It's called the Heisenberg uncertainty principle.
Okay, back to Schrödinger's equation.
Right. So Schrödinger was trying to come up with this equation
Yeah.
to describe the behavior of these wave-like particles.
And how did the Davisson-Germer experiment help?
Well, remember how they showed that an electron's wavelength is related to its momentum?
Yeah.
That relationship, that connection between wavelength and momentum. It was a crucial piece of the puzzle for Schrödinger.
So their experiment, it not only provided evidence for wave-particle duality, it also contributed to the development of one of the most important equations in physics.
It just goes to show how interconnected science is.
Absolutely. Now, we've talked a lot about the experiment, but what about Germer himself? What did he do after this groundbreaking discovery?
Well, he continued his research at Bell Labs, but his focus shifted somewhat.
In what way?
He moved away from purely theoretical work and started to focus more on applied research.
So more practical applications of physics.
Exactly. Schneppat's essay mentions his work on things like vacuum tubes and electrical contacts.
Which are essential components
Yeah.
for all sorts of electronic devices.
Right. So he went from probing the mysteries of the universe
Yeah.
to improving everyday technology.
That's pretty cool. It shows his versatility as a scientist.
Absolutely. He wasn't just a theorist. He was also a skilled experimentalist.
Yeah.
And an innovator.
Well, I think this has been a fascinating deep dive into the life and work of Lester Germer.
It's a story that highlights the power of curiosity, collaboration, and a willingness to embrace the unexpected.
And it all started with a simple question. How do electrons bounce off a nickel surface?
And who knew that that question would lead us to one of the most mind-blowing discoveries in the history of physics?
It's a reminder that even the smallest particles can hold the biggest secrets.
And that the world is full of surprises.
So we have this idea that an electron can be a particle and a wave. What does that even mean? Does that mean everything's kind of blurry, like baseballs and planets are also waves?
Well, it's true that quantum mechanics says all matter has wave-like properties. But these effects are most noticeable at the atomic level. The larger an object gets, the smaller its wavelength. So for something like a baseball, its wavelength is so tiny, it's practically undetectable.
Okay, so it's there, but we can't really see it. Still, it's pretty wild to think that everything, even us, might have this wave nature kind of hidden beneath the surface.
It definitely challenges our everyday intuition.
And speaking of real-world implications,
Yeah.
Germer's work on wave-particle duality wasn't just some theoretical idea. It led to some incredible technologies, like the electron microscope.
Oh, absolutely. The electron microscope, it's revolutionized so many fields. We can see things we could never see before. Viruses, the structure of cells, the arrangement of atoms.
All thanks to this understanding of electrons as waves.
Exactly. It's a perfect example of how fundamental research can lead to practical applications that change the world.
It's amazing to think that a seemingly simple experiment with electrons bouncing off nickel could have such far-reaching consequences.
It really highlights the power of scientific curiosity. You never know where a discovery might lead.
Well, I think that brings us to the end of our deep dive into the life and work of Lester Germer, based on Yorgo Schneppat's essay. We've covered a lot of ground today, from his early life and education to that groundbreaking experiment with Clinton Davisson, and even his later work at Bell Labs.
It's a story that showcases the beauty and the strangeness of quantum mechanics.
And it leaves us with a lot to think about. If even something as tiny as an electron can defy our classical notions of particles and waves, what other mysteries might the quantum world hold? What do you think?
That's the million-dollar question, isn't it? And that's what makes this field so exciting. There's still so much we don't know, so much left to explore.
Thanks for joining us on this journey into the quantum realm. We hope you enjoyed it. Until next time, keep exploring.